Okay. As we will see, there were many papyri that were found by the Egyptologists that contains mathematical information. And one of, as we will see in our lecture, but the one that was very important and very well known worldwide is called the Rhind Mathematical Papyrus. We will talk about it in more details later. So in fact, the person who introduced this papyrus and translated for the first time is called Arnold Chase, and he wrote in his article, I venture to suggest that if one were to ask for that single attribute of human intellect which would most clearly indicate the degree of civilization of a race, the answer would be the power of close reasoning, and that power could be best determined in a general way by the mathematical skill which members of the race displayed. Judged by this standard, the Egyptian of the 19th century before Christ, that means 4,000 years ago, had a high degree of civilization, because he identified that the civilization is well defined by the power of thinking and the power of reasoning. And another person, who is Professor Gellings, he wrote a very famous book about the mathematics in the time of the pharaohs, and this would be one of our references. In his book, he explained many things in this papyrus and different other papyrus, and he quoted in his book also that the brain power which is evinced by the building of the pyramids is in no way inferior to that of the great engineering of present days, and that the Egyptians had attained all the essentials of civilization as fully developed as our own as early as 3000 BC. Because, as I said, 3000 BC, they have built their pyramids with great precision, as we will be talking about. So, the first part, I will talk about pyramids and its relation to sciences and beliefs. As I said, the building of a pyramid is not just putting one stone on the top of the other, but it has lots of knowledge behind it. So this is a cross-section of the Great Pyramid of Egypt, and in fact Professor Petrie from England has made some measurements of this pyramid at the end of the 19th century, and he found miraculous mathematical and engineering knowledge behind it. So in fact, in order to build such a pyramid, you have to know well the science of astronomy, because this pyramid is oriented towards the true north and true east and true south and true west with very great precision, and in order to do that you have to have astronomical skills so that you can build such a pyramid with this precision that we have. Also, another thing is that they had found that the pyramid is built with very great precision in its squaring. It's a good square, and it has good right angles, exact right angles, and it has the perfect slope for a pyramid, and so on. So you must know really geometry, and remember that this pyramid, which is about 150 meters high, does not have its axis twisted to this way or twisted to the other way. There is no error in building such a thing, so it must contain a good amount of knowledge in geometry. Also, as we will see the background of the geometry, we have a good knowledge of mathematics. And also, one of the puzzling questions is that the blocks of the pyramid are blocks of 2 or 3 tons. They are heavy, and there are some blocks that are on the ceiling of the inner halls of the king and the queen that we will see, that has blocks that is 20 tons of weight, so they are very heavy, of granite. And they brought these blocks from Aswan on boats. So in order to bring a block of stone of 20 tons and put it on a boat, the boat must be well designed and they should know the laws of buoyancy, so that when they put this huge stone on the boat, it wouldn't sink. And they wouldn't, we cannot imagine that they did it by trial and error. They must have well calculated, because if you do it by trial and error, you lose many pieces of huge stones, and then till you get to the final solution. So that shows that the ancient Egyptians really were very knowledgeable also of physics and soil mechanics. If we are going to build any high-rise building now today, then we should really make sure that the soil underneath this building can support this heavy weight. So we do normally soil mechanic tests on the ground before we do the building, so that it would be late after we build the building, it falls down. So certainly for a building like the pyramid, and it's one of the biggest buildings in the world, you cannot build it without making sure that the ground can support such a building. And we have some evidences that they did some tests on the soil before they built this pyramid. And finally, they must have good knowledge of mechanics in order to raise these blocks of stones, that is 2 and 3 tons, to the different levels up to 150 level. In order to do it today, we have to apply cranes that are very well sophisticated and very well developed, so that we can do a similar thing. And in fact, the Japanese have done a similar experiment in order to build a small pyramid to see what is the problems behind that. And they found really that in order to build a great pyramid, there must be a good knowledge of mechanics. In addition to that, you can imagine that this pyramid, as we know from history, it was built over about 20 years, and there were 20,000 workers involved in building the pyramid. So you can imagine, if you have today a company that has 20,000 workers, and the company is existing for 20 years, how much effort of management should be applied in order to well manage this company, in order to have the work done properly. And the last thing that we see behind this pyramid is the belief, because building the pyramid at that time, of course, if you go into the belief of the ancient Egyptians, and in many other nations, they were considering that the king is a representative of the divine and a representative of God. So that was a national project behind which all the nations were passionately working in order to achieve it in the best way, and they consider this achievement as part of their belief and as part of their knowledge. So quickly, you have seen that during your visit to the center, the pyramid is built on an area of 13 faddan, and the number of stones is 2.3 million of stones. And also the casing of that pyramid is so straight, so truly square, to the extent that there is an error of 1/50 inch over 30 feet. So it's really very precise building. And also its accuracy, as we said, it's well aligned to the true south and true east and true north with very great precision. And also in the dimensions of the pyramid, we have the base. At the time of the pyramids, the measurement that was used is the cubit, which is used by the farmers in Egypt up till now. I mean the dimensions of the person. The smallest unit is the finger, and then the palm, which is 4 fingers, and then the cubit, which is 7 palms. So in fact, they were using the cubit, which is the unit of the arm, which is dira' bil Arabic. The farmers are using it up till now. So the base was, in fact, was about 440 cubits, and the height was 280 cubits. And when we make division of the base to the height, then we find that it gives the ratio 22/14, which is pi by 2 exactly. And also if we divide the length of the side by the base, then it gives 1.61h, which is the golden number that was used by the Romans. So in fact, in the building of the pyramid, there is embedded the international fixed values, which is pi and phi, and we will see in their mathematics they know about it very well. So now we come to the mathematics of the ancient Egyptians. For me, the scribe is a very good, important idol or example of icon of the ancient Egyptians, because that means they were really documentarists. You see any scene at the time of the ancient Egyptians, and in this scene, you always see on the side a scribe sitting, making notes of everything happening, whether they are cultivating, whether they are building, whether they are doing anything, then there is a scribe doing that. And that's why the ancient Egyptian civilization left behind it lots of documents, whether engraved on the walls of the temples or in the papyri that we got it. After the end of the ancient Egyptian civilization about 2,000 years ago, we lost contact with the language, and we lost contact with what was written on the walls and in the papyri, till we found about 200 years ago the Rosetta Stone. And the Rosetta Stone is a piece of stone from the time of the Greek period, when Egypt was occupied by the Ptolemies, and it has the same text written in 3 languages, or 3 types of writing. In hieroglyphic and demotic. In fact, it's like in Arabic we have riqa and nasakh, 2 types of writing. One of them is quick writing and the other one is the exact one. So the ancient Egyptians, they have the hieroglyphic, which is the official way of writing and the royal way of writing. And then they have 2 other way of writings that they call it hieratic and domatic, which is a quick way of writing, as we will see. And then we have a third type, a third line, which contains the same text written in Greek language, because that was at the time the Greeks were governing Egypt. So from this we have a text that is in 3 languages. We tried to compare between the 3 languages, and the person who did this comparison was Champion, as you all know. And finally, he started the deciphering by knowing that at the time of the ancient Egyptians, when they write a name of a king, they normally put it inside a cartouche. A cartouche is this shape that we call it cartouche, and so if we find in the text any name that is of this form, then that means this is the name of a king. From the hieroglyphic, from the Greek language, he recognized that this is really the name of Ptolemus, the Greek ruler of Egypt, or the Ptolemy ruler of Egypt. Then he looked he found it in the Greek text, and he looked for the cartouches in the hieroglyphic text. He found this cartouche, then he said this must be Ptolemus. And then they started ciphering, then this became the P, and this is the T, and this is the O, and this is the N, and this is I, etc. And this is S. And then from another cartouche of Cleopatra, as they started with the cartouches, and then they worked on the text itself, and there is a technology for doing that across history, is that you look for things that are repeated most of the time statistically. Then this must be and, for example, a word like and is repeated normally, most likely, and so on. And from that, he deciphered completely the language. But he found that this language is different from the language that are normally known. It's that it's not alphabetical, but it's syllabical. That means it has syllables of 2 or 3 vowel or 2 or 3 voices together, or letters together. So some of them has single value of letters, and some has 2, and some has 3. These examples that are here are single value, like in any alphabet, the A, the B, the C, and so on. So this represents the A, this represents the M can be written in 2 ways, this represents K, etc. And look at this, very important, it represents R. This is the mouse. Of course, all the representations are parts of human bodies, or parts of animals, or parts of birds in general. And then he found that there are many other things that has more than one pronunciation, or one letter pronunciation. Like for example, the word that we all know, Ankh, in the name of Tutankhamun. Ankh is one word, is one letter that has 3 letters in it. Ankh, Ain, Nun, Kha. Or this one, for example, here is Kheber. Kheber, this is in the name of Tutankhamun, also in the hieroglyphic name. For example, another thing that is known, Nefer, like in the name of Nefertiti and Nefertari. Nefer, NFR is just one sign, Nefer. And this sign here is Mes, that we find in the word, in the name of Ramses, Mes. So it's 2 letters together in one word. And remember that today, on our mobile, we use the same technique. When I write that I'm going to you, then I write the letter 2 in order to replace TO. So I write 2 to replace TO, etc. So that was the discovery of, and these are some of the names of the kings that are written in hieroglyphic. Let us recognize some of them. This is Khofu, this is Kha-O-F-O. These are all single vowels. Then let us see if there is Ramses, or this is Pipi, this is P-I-P-I, etc. This is Nefer-Ka-Ra. There is a king called Pipi the First, and his first name is Nefer-Ka-Ra. So this is Nefer, this is Ka, this has 2 values, and this has 3 values, and this is Ra, the god of sun, and he's always represented by the circle, which is the sun, etc. So now we come to the first part of our mathematics, is how they represented their numbers. As you know, in the Roman way of writing numbers, we have the 1 is 1 stroke, the 2 is 2 strokes, and then the 10 is an X, and so on, and the 100 is C, etc. So it's exactly, or very, very similar to it, is the ancient Egyptian hieroglyphic way of handling of numbers. But remember that the ancient Egyptians is much older than the Romans. The ancient Egyptian civilization started 5,000 years ago. The Roman Empire started 2,000 years ago, or 2,500. So the 1 is 1 stroke, the 2 is very simple, of course, 2 strokes, 3 strokes, 4 strokes, 5 is 5 strokes, etc., up to 9 strokes. It's very simple. And then remember that in the Roman system, the 5 is represented by the letter V that we know now. But at the time of ancient Egyptians, it was separate like this. And then there is a sign for 10, which is this sign, which is like the letter U inverted, which is, remember that in the Roman system, it's the X in this case. And then the 100 is this one, and then the 1,000 is the lotus flower, and then 10,000s, and then 100,000s is a bird, and then a million is somebody raising his hands and then as if he's saying thanks for God. You got a million. So this was the way that they represented their numbers. If they want to write 23, they repeat the 10 2 times and the 1 3 times, that becomes 23, etc. We will see some examples of this later. And then, as I said, there are 3 types of writing, but I'm talking now about 2 of them because the second is the one that is used in most of the papyri. So you have here the hieroglyphic that we talked about, from 1 to 9, and then tens from 10 to 90, and then hundreds from 100 to 900. And then in hieratic, I said hieratic and demotic is a language for quick writing. It doesn't put details, it abbreviates the details into simple writings. So you have here the 1, 2, 3, and remember that this is close to the Arabic 3 that we write today. And then 4, and then 5 and 6. And look at the 7. It became a sign. The 8, in fact, sometimes the 4, they write it a single horizontal line because it evoluted from 4 strokes to 4 points to a horizontal line. And then the 8 is 2 horizontal lines. And then this is the 9, and this is the 10. Look at this 10. Remember this figure very well because we will see it later on in many things. So it became signs instead of repetitive things. So these are the numbers. Then come the fractions. How did they deal with fractions? The ancient Egyptians, they dealt with what we call unit fraction. Unit fraction is 1 over. They have 1/3, 1/4, 1/5. And in order to write 1/3, they write 3, and they put on the top of it the letter R in hieroglyphic that we saw before, which is of this type. So if you find any number and then it has this sign on the top of it, then it becomes 1 over. So it's 1 over 4, 1 over 5, 1 over 6, 1 over 7, etc. and 1 over 10. And then in hieratic, then they invented signs, as we said, but sometimes for the half, for the third, for the fourth, these are new signs, and then for 1/5, they write 5 in hieratic and they put a dot on the top of it, and so on. They go on and on. They put R on the top in hieroglyphic, and they put a dot, in fact, in general, in hieratic, except for these signs. With one exception also is, there is a fraction that they know very well, which is 2/3. They used a lot, and so it's 2 over 3, it's not 1 over 3, and they used it a lot in their mathematics. It has this sign in hieroglyphic and this sign in hieratic. Did you study quickly, I mean during your secondary school, did you study computers? A little bit? Yeah. So you know the computer works in binary system. And when the computer works with fractions, it works with binary fractions. And binary fractions are 1 over 2, 1 over 4, 1 over 8, 1 over, and it never works with 2 over something or 3 over something. But finally, after the computer does its operations in its electronics, we transfer it into the way we know it, into the decimal numbers we know. Okay, so now we come to how they manage their mathematics. First, the simplest thing is how to make addition. Addition in hieroglyphic is very simple. If you want to add 24 plus 53, then this is 24, 2 times 10 and 4. And look here, we are writing from right to left because the hieroglyphic language is what we call Semitic language, is belonging to the family of languages of the Middle East, like Arabic and Hebrew and Aramaic, etc. And then if you have 53, then you have 5 tens and 3 ones. And then if you want to add them together, if you put them one under another, then you read the result immediately, in fact, because this is 7 tens and this is 7 fours. It only becomes 77. It's as simple as that. So you just put 2 numbers, one under the other, and it reads the result immediately.
You should go back to hieroglyphics. So
Yeah. You will see. You'll be convinced more after a while. So let us now talk. This I will go quickly in it because you should know it. The difference between decimal number and binary number, because we will see how the ancient Egyptians made use of that. The decimal number, if we have a number like this, then depending on the position, the first position is unit, the second position is 10, the third position is 100. So in fact, the 2 is in fact 2 times 100, and the 5 is 5 times 10, and the 6 is 6 times 1, and the point 3 is 3 times 1 over 10, and then the second position is 1 over 100, etc. So in fact, this number is the addition of this combination, which gives what we know now by heart is 256. We say 256, but in fact it's 2 and 5 and 6, etc. And then in the binary numbers, it's exactly the same idea, but instead of have 10 different values from 0 to 9 for every position, we have only 2 values, either 1 or a 0, as you all know. And the first position is equivalent to 1, the second position is equivalent to 2, the third position is equivalent to 4, the fourth position equivalent to 8, etc., as you all know. So this number in binary, 101.1, is equivalent to 1 times 4, plus 0 times 2, plus 1 times 1, plus 1 into 1 over 2, plus if there is another fraction, 1 over 4, plus 1 over 8, etc. So, which gives the result in decimal equivalent to 5.5. So you know, I think this very well, you don't need to explain it. But I just introduced it in order to show you how the ancient Egyptians think. Now we come to the multiplication. If we want to do a multiplication in decimal system that you all know, then if we want, here is an example, if you want to multiply 21 by 13, what does we do? What do we do? We multiply normally the first number by the whole number, and then we multiply the second number and shift it, and then we add them together. So 3 times 21 is 63, 13 times, 1 times 21 is 21, and we shift it because it's in the 10th position. We shift it 1 position, and then we add them together and we get the result 273. So, but this operation that we were doing it when we were young, it necessitates many things. Number one, to memorize the multiplication table. I have to memorize in my head that 5 times 6 is that much, and 3 times 4 is that much, and so on. And the second thing is that it's an operation that involves series of add and shift operations. We add and shift and add and shift and add several times. And remember that this idea of multiplication table was just invented about 500 years ago. It was not known before that. And if we do multiplication in binary, it's the same thing. But look here very carefully. If we have a number 13, we want to multiply it by 21. In the computer, the 13 is transformed into binary, into 1, 1, 0, 1. And the 21 is 1, 0, 1, 0, 1. Okay? And then when we want to multiply them together, for the binary multiplication, it's like the decimal multiplication. We multiply the first digit, which is 1, by the whole number, it gives this one. And then we shift, multiply the second digit, it gives 0. Multiply the third digit, it gives this number, and we shift it twice. Multiply the fourth one, which is this number, and we shift it 4 times. And then we add them together, it gives finally this one. And this number, digital number that we got at the end, when we transfer it to decimal number, it becomes this 273. So remember that this 1101 is in fact, the first one is equivalent to 1, the second one is 0, the third one is 4 in decimal, the fourth one is 8 in decimal. And then the values after multiplication here of every line is equivalent to the first number is 21, the second number is 0, third number is 84, fourth number is 168, etc. So this is in fact inside the computer we have all things going in binary, and then the computer at the end we transfer these binary numbers into decimal numbers, and we get the result. So now let us see how the ancient Egyptians deal with this problem. The ancient Egyptians, the main important thing in the way of thinking of the ancient Egyptians is that they were systematic. They put a rule, they put what we call in computer algorithm, and they follow this algorithm clearly. Remember that at that time we don't know the multiplication table, we don't know how to add and shift and all these things. So if I want to multiply 13 times 21, that's what we do. Systematically, number one, we build this table, a binary table that has in this column 1, 2, 4, 8, 16, 32, 64, etc. And then we stop the table at at the level depending on the numbers we are dealing with, as we will see. And then the second step, we put the two numbers we want to multiply them together on the top of the table, 13 and 21. And it could be any two numbers. And you do this exercise yourself, is that you pick two numbers and put them and try to do the exercise yourself. And then the third step is that they try to decompose the 13 into these components. So they take 16 is higher, 32 is higher, 64 is higher, so we don't take any of these. 8 is lower, then we take 8, and then we take 4, 8 plus 4, that makes 12, yes, but it's not yet 13. If we add 2, that makes 14, then it exceeds the 13, we don't take it. And then finally, we take the 1, that makes 13. So the 13, we decompose it into 8 plus 4 plus 1, okay? If it were 12, for example, we add to 4, and then it makes 12, and that's all. And so on. You do this exercise for yourself, as I'll tell you at the end of the thing. And then this is the third step. The fourth step is that they take the other number, 21, and they put it here, and then they double it, and then they double it, and then they double it. They double it several times, okay? And doubling a number in hieroglyphic, as you have seen, is adding the number to itself. And it's a very simple mathematical operation. You add the number to itself. So you add 21 to 21 makes 42. You add 42 to 42 makes 84. You add 84 to 84 makes 168. And then you look at this table, and the numbers that correspond to the numbers that are highlighted here, you choose them like this. So the 8, you take the 168. The 4, you take the 84. The 1, you take the 21, and you take them apart, and then you add them together, and this is the result. That's how the ancient Egyptians did their multiplication. And look at this table carefully. Here you have 1 and 4 and 8, and here you have 21, 84, 168. And again, this is the binary multiplication of the computer of the same two numbers. Here you have equivalent to 1 and 0 and 4 and 8. And here you have 21, 0, 84, 168, and you get the same result exactly. So sometimes at the beginning, when they discovered how the ancient Egyptians did their mathematics, in the beginning of the 19th century, the computers were not yet invented. And they said, oh, they do very simple operations and very simplified operations, and they were not that intelligent. And then after a while, they discovered it's just the computer is working exactly in the same way. So that means, I don't want to say that means that the ancient Egyptians invented the computers. But what I mean is that the way the computer works today is exactly the same way the ancient Egyptians were doing their mathematics 5,000 years ago. So, in doing this, there is no memorization of multiplication table. There is no need for add and shift operations. Doubling is just adding a number to itself. And finally, multiplication is reduced to simple additional operation. So, as you can see, it's a very simple way of operation. Now we come to the other operation, which is division. If I want to divide two numbers, and in order to generalize, these two numbers are 31 divided by 3. In order to generalize, I've chosen a number that is not a multiple of 3. So 31 is not a multiple of 3. So we know the result. If we divide 31 by 3, this gives 10, and there is a remainder 1. Yes? Okay. So how did the ancient Egyptians do it? It's exactly the same way they did before, but in a reversed operation. Number one, they put this series that we all know, 1, 2, 4, 8, as I said before. And number two, they put the two numbers on the top of that table, but they put the higher number to the left. In the multiplication, it doesn't make a difference whether they put the higher number or the lower number. But in division, it's better to put, you should put the higher number to the left and the lower number to the right. And then you make, as I said before, doubling. You take a 3 and double it becomes 6, and double it becomes 12, and double it becomes 24. And then we go from the right column now, not from the left column, is that we decompose the 31 into its components. So 24, we add to it 12, it becomes 36 more than 31, we don't take it. We add to it 6, it becomes 30, yes. And then if we add 3, it becomes 33, it's higher than 30, than 31. So then the result is 30. It's not, these are the components of the 31. And then on the opposite side, we mark the numbers that is equivalent to the one that are marked in the first column or the right column. So we mark the 8 and the 2 in this case. And we add them together, and this is 10. And this is the result. Dividing 31 by 3, the result is 10. And then we subtracted the 31 from 30, and this is the remainder. So from this table, we get from here the result, and if there is a difference between these two numbers, this represents the remainder. This is how they do a division with a remainder. So I think they were very clever in a very simple way and in a very systematic way. So that we were talking about numbers. Now if we talk about fractions, as I said before, at the time of the ancient Egyptians, they used unit fraction, which is 1 over any number, 1 over 2, 1 over 3, 1 over 10, 1 over 100, 1 over 256, etc. This is very similar to what the computer is doing, because the computer does binary fractions. It's 1 over 2, it's only binary numbers, unit fractions, but only binary numbers, 1 over 2, 1 over 4, 1 over 8, 1 over 16. Again, we find that there is a similarity between what the computer is doing and what the ancient Egyptians were doing in their fractions. The only difference is that the ancient Egyptians used any unitary fraction, but the computer uses only binary fractions, which is 1 over 2 or 1 over 4, etc. So, in fact, as we will see, as it happens even in the computer, if you want to take 3 over 8, for example, then we say 3 over 8 is equivalent to 1 over 2 plus 1 over 4 or something like that. So it gives 3 over something, but we always decompose it into unit binary numbers. So the ancient Egyptians did the same thing. If they want to do more complicated division or fractions, like 2 over a number, they have constructed a table which is very complicated, we will see, and in any case it was very puzzling to several scientists, mathematicians, to see how they arrived to it. The table, it talks about, we will see it later in the second part, it talks about 2 over any odd number, 2 over 3, 2 over 5, 2 over 7, 2 over 9, 2 over 11, 2 over 13, etc. Up till 2 over 101. As an example of that, let us take this line. This is in fact the hieroglyphic language or hieroglyphic table that we rewrote it into our normal decimal tables. So 2 over 13, this table it reads like that. It's 2 over 13 is equivalent to 1 over 8 plus 1 over 52 plus 1 over 104. 2 over 13 is 1 over 8 plus 1 over 52 plus 1 over 104. Another example, 2 over 69 is 1 over 46 plus 1 over 38. And you add them together, you do this exercise, you will find that it is equivalent to 2 over 69. And so on. But if you do this exercise yourself, if you want to decompose 2 over any number in order to get it into unit fractions, you will find that there are many possibilities to do that. I mean, maybe I show, yeah. For example, if you wanted to make 2 over 45, if you run a computer to do this decomposition, you will get 1,967 different decompositions. 7 of them in 2 terms, 1 over something plus 1 over something, and 3 of them and 134 combinations of 3 terms, 1 over plus 1 over plus 1 over, and then finally 1,826 different combinations of 4 terms. So how did they choose between these all possible combinations, the combination that they have put into the computer system or into the table that they have produced? This is very interesting, and this is one of the questions that we will explore maybe in the second part, is that how they came to this table. In fact, when they invented the computers, because this table was discovered, I mean this papyrus and the table and so on was discovered at the end of the 19th century and beginning of 20th century, and then they said, okay, let us try to do it with a computer. So they did a computer program and they ran it in order to get all the possibilities and finally reduce it to the one that is selected here. And this computer took about 6 hours in order to do the calculations in order to reach this. But remember that at the time of the ancient Egyptians, they didn't have this kind of computers or this kind of machines. So how they did it? This is one of the mysteries that many of the scientists or mathematicians are working on it in order to try to find out a way or an algorithm of how to reach this multiplication table. So, in fact, we will come to this later. So here is the 7 2 terms decomposition of 2 over 45. So in fact, it's equivalent to 1 over 24 plus 1 over 360, and it's equivalent also to 1 over 25 over this. Here are all the so in fact, you have here 1 finger, or centimeter in our days units, 2 fingers, and here they have a finger here, 2 fingers, 3 fingers, and then a palm. You have a palm here, which is 4 fingers like this, and then you have a palm with a finger, which is 5 fingers, etc. And then on the other side, they give the fractions, like in centimeters, we give millimeters. But remember that the ancient Egyptians were talking about unit fractions. Unit fractions is 1/2, 1/3, 1/4, etc. So they divide the finger or the unit of measurement into 2 halves, and it becomes 1/2, 1/3, 1/4, etc. So it corresponds to the way of thinking of the ancient Egyptians. They go up till 1 over 16, which is fascinating. As you see, it's a masterpiece that we have many of them in the different museums, and we have, of course, some of them in the Egyptian museum itself. So they used the ruler that, like the one we are using today, in centimeters and etc. but their ruler is, its length is a cubit, which is about 50 centimeters or half a meter, and it's divided into 28 fingers, and the 28 fingers is divided, as we see, into unit fractions, 1/2 of a finger, 1/3 of a finger, 1/4 of a finger, etc. So we come now to the Rhind Mathematical Papyrus, and it's abbreviated into RMP. In fact, we have found 6 papyri up till now that are dealing with mathematics. In fact, we found thousands of papyrus in different museums now. So there are 6 papyri that are dealing with mathematics. Unfortunately, none of them is in the Egyptian museum. All of them are in the different museums of the world. The first one is called Reisner Papyrus. Reisner is an Egyptologist who worked in Egypt a lot, and he's from Boston, and this papyrus now is in Boston Museum. And there is Moscow Mathematical Papyrus, because it's now in the Museum of Fine Arts in Moscow. And there is Khaun Papyrus, which is in London, and the Egyptian Mathematical Leather Roll in the British Museum, and the Rhind Mathematical Papyrus, which is the most well-known papyrus of all of them, and it's in the British Museum, and that's the one that you have seen at Kaltnacht when you did the visit. And finally, the Berlin Papyrus, which is in Berlin. They are called Berlin and Moscow and so on, but they are Egyptian papyrus. They name them after the places where they are put. So this is the dating of these papyri. This is the timeline of the Egyptian history, starting from the ancient Egyptian Old Kingdom, Middle Kingdom, New Kingdom, up till the Arabs. And then here is the time when when the Reisner Papyrus was written, and this is the time when the Rhind Mathematical Papyrus, and this is the Berlin Papyrus, etc. So all of them are more than 1,000 years BC. That means 3,000 years back from now. This is part of the Rhind Mathematical Papyrus. The Rhind Mathematical Papyrus, as we will see, is about 5 meters long. And this is a famous page of this papyrus, which contains 6 problems. One of them is the area of a rectangle. Another one is the area of a circle. Another one is the area of a triangle. And the third one is a truncated triangle. And then a similarity of triangles, etc. And as you see, the organization of the problems is fascinating. They have black lines separating the problems, and the title of every problem is always written in red, and then you have the statement of the problem, and then you have the solution of the problem. So it's very well organized, and you have a sketch of the problem showing you he's talking about what. So it's exactly the same way that we are dealing with mathematics today. So this papyrus, Rhind Mathematical Papyrus, was found in 1855 in Luxor. I mean, it was rediscovered or refound, and it was bought by a British tourist that came to Egypt with the name of Rhind. That's why they call it Rhind Mathematical Papyrus. And then he gave it to the British Museum later on. The dating of this papyrus is from 16th century BC. That means about 3,500 years back. And it's now in the British Museum, except a small part is in the Brooklyn Museum in the United States. Its length is about 5 meters, 5 meters and something. And the papyri, did anybody visit the Papyrus Museum of Ragab Museum of Papyrus? No. So in that museum, they fabricate papyri in a modern way that we don't know exactly how the ancient Egyptians did it. So they normally do it in sheets that are almost like the A3 sheet, and then they stick these sheets together to make a scroll finally. So these are sheets. The papyrus of Rhind Mathematical Papyrus is made out of 14 sheets, and these are stick together in order to make a scroll that is 5 meters long. It contains 87 problems, like the 6 problems that we have seen. And it has a cover page, like any book we know now. It has a cover page that gives the title and the dating and the name, the author, etc. So it has the same organization. And also it has 2 parts. Part of it, half of the papyrus, is this 2 over fraction over tables that we have seen. And it has a set of problems, about 87 problems, 60 problems on one side of the papyrus, and the rest of the problems on the back of the papyrus. Although you have seen it at the visit to Khaun, but I'm putting some stress on some parts of it. As you have seen it there, of course, on the 9 screens with a length of about 15 meters. So here now the Rhind Mathematical Papyrus is made of 2 parts. One of them, as we can see here, are in the British Museum, and then there are some fragments in the middle, which is in Brooklyn Museum in USA. The question is, how did we know that these fragments are part of this papyrus? It's as simple as that. As I said, the papyrus has 2 parts. Part of it is this table, the fraction table, and the table goes from 2 over 3 to 2 over 5 to 2 over 7, etc. And so we found that the fractions that are here, the fragments that are here, contains continuity of this table. So it's part of this fraction table. And then this is the back of it, they'll call it verso. And the total length of it is 5 meters. So we have here a system that we can see it. This is the title page that I told you about. It has, as the ancient Egyptian always do, it has the title in red. This is the cover page. It has a title in red, and it has a dating, the year that it was written in, and then it has name of the scribe that wrote it, and so on. So it is fascinating, in fact. And then we can have some look here with this magnifier on the different parts. You remember the 1 and 2 and how we write the numbers in hieroglyphic, in hieratic. So you see here, this is the start of the fraction table. I'm not going in details of it now, but just to show you the numbers that we were talking about in hieratic is now used in order to write these tables that are here. And then, as I said, the papyrus goes on and on for 5 meters long. But in any case, as maybe I said before also, that the papyrus is made out of sheets, about 8 sheets. So here you can see the division or the separation of these sheets. This is one of the sheets here, and then it's fixed to another one and fixed to another one to make the whole papyrus. So it goes on, and as I said, part of it is just these fragments, which contains continuity of this table here. And then another part, which is, as we said, 87 problems. The mathematicians, when they work on these problems, they have divided them, separated them and give them numbers. So now when I'm talking about the problem number 50, every mathematician that is working with Rhind Mathematical Papyrus knows what I'm talking about. So for all of us, problem number 50 is talking about area of a circle. Problem number 49 is area of a rectangle, etc. And then these problems that are here are for the pyramids, solution of pyramids. The volume of a pyramid, the slope of a pyramid. The ancient Egyptians, they have a notation for the slope, which is equivalent now to the tangent and cotangent, etc. So this is, as we said, the first one of the pages that is very famous, which is contains 6 problems. They always show it everywhere. And remember again that this is 1,500 years BC, and Pythagoras was about 400 BC. That means this is 1,000 years before the Greek scientists. 1,000 years before the Greek scientists. So this is the area of a rectangle, area of a circle, area of a triangle, area of a truncated triangle, etc. And as an example of it, as you have seen maybe at CalcNet, is this problem of a triangle. The importance is the organization of the problem. Is that here you have a separation line in black between every problem, and then you have here the title in red and the statement of the problem, and then you have the solution here, and you have a sketch like exactly any modern book of mathematics today. And so the title here is example of calculating the area of a triangular land. And remember that this is the sign of 10 that we were talking about in hieroglyphic, and this is the sign in hieratic, in fact, and this is the sign of 4. So it's a triangular land of if you have a triangle of height 10 chet, and this is the sign of 10 here, you can see it, and height 4 chet, and this is the sign of 4 here. So what is its area? Exactly the same way we write our problems today. And then take half of the base 4, this gives you 2, so that you can square the triangle, so that you can make a triangle equivalent to a rectangle. And this is exactly the proof that Euclides gave 1,000 years later. That he says, if you have a triangle, then you make it equivalent to a rectangle, and then you calculate the area of a rectangle. And then you multiply, it's half of the base multiplied by the height, so you multiply 10, which is the height, by half of the base, which is 2, and this gives you the area. So, in fact, this is the way the ancient Egyptians were thinking, is that they tried to square everything. If they have a triangle, they try to find out the equivalent rectangle to this triangle and get its area. If they have a truncated triangle, they find the square or the rectangle that is equivalent to this. If they have a circle, they do the same thing, is that they find out what is the best fit of a square that has the same area of a rectangle, of a circle. So they came to a very simple conclusion. We know by heart that's pi r squared, and you can calculate it. If this is, so they said, if we have, this is the diameter d, then you find a square that has a side which is 8/9 d, and this is the best fit. So let us calculate together this example. If we have, for example, a circle of diameter d equals 9, then pi r squared equals pi into 4.5 squared. So can anybody do this calculation and get the result? 63. Yeah. This is the result. Huh? Okay. Okay. Look at that now, what the ancient Egyptians do. They say if the diameter here is 9, take 8/9 over d, that makes the side equals to 8. Multiply 8 times 8 in order to get the area, it's 64. Look at the result. Fascinating. Huh? They get a result with less than 1% of error by a very simple formula. If you have any circle of certain diameter, then you take 8/9 of this diameter, this will be the side of the equivalent square. No, you square it, you get the result. It's fascinating. And remember that this pi, it doesn't have any physical meaning, but this demonstration gives a real physical meaning, how you just push the circle to make it a square. So what's the best square that can fit the circle? Okay. So now we come back to a little bit of details of the fraction table I was talking about. You remember this fraction table? I said that they used these unit fractions 1 over, and then they found out that the ancient Egyptians did this table for 2 over any odd number, 2 over 3, 2 over 5. 2 over 5 is 1 over 3 plus 1 over 15. 2 over 13 is 1 over 8 plus 152 plus 1 over 104. So in fact, what we did, or what the scientists did, is they looked at this table and they looked at the combinations that could be possibly give the same result, and found out they came to certain conclusions. Here are the conclusions that they got to. The first conclusion is, of all the possible equalities, those with the smaller numbers are preferred. Which means that if you get terms like this, then we don't like the 100 over 360 because this is too high for 360, or 100 over 225, but 100 over 90 is relatively small, as we see. So this is the first conclusion. And then the second conclusion is an equality of only 2 terms is preferred on 3 terms, and 3 terms is preferred on 4 terms, etc. That means if you have a result of 1 over, like here for example, for 2 over 45, you can have plenty of ways to do it in 2 terms, and in 3 terms, and in 4 terms. That means 2 fractions or 3 fractions that add up to the same thing, or 4 fractions. In this case, we prefer the 2 terms. We prefer the lower one that contains only 2 terms. And then the third thing is the unit fractions are always set down in descending order. As you can see, we put 1 over 3 and then 1 over 15 and then 1 over 28. It goes, we don't put, they always go in order. Like here, for example, 1 over 8 plus 1 over 52 plus 1 over 104. They don't say 1 over 8 and 1 over 104 and 1 over 52. They go in descending order. And then concept of precept number 4. The smallness of the first number is the main consideration. They want to have it as small as possible. Like in this example, this is 1 over 30. But if they go to 1 over 24, which is a little bit smaller than this, then this number becomes very high, etc. And then the last thing, even numbers are preferred to odd numbers. So they tried to figure out from this table what happened with the thinking of the ancient Egyptians. And based on that, they have run an electronic computer to calculate all possible combinations that of unit fractions that can give the results. It came out to about 22,295 combinations, and from this they applied the 4 concepts that we talked about, the 5 concepts that we talked about, and they came more or less to this conclusion. And this computer took, as I said, about 6 or 7 hours in order to make this calculation, to come to the conclusion that the ancient Egyptians did about 4,000 years ago. So it is fascinating and it's intriguing. So as an example of that, we have this number, as I said, 2 over 45. It can have 1,967 decompositions in 2 terms and 3 terms and 4 terms. And finally, we find that it's preferable to have the 2 terms because these are too much terms. And these 2 terms, here they are, the 7 2 terms are like this. And they have chosen the one that gives an odd number, an even number here, and also as relatively a small number as possible, and also here as a small number as possible, etc. So they found that the best fit is 1/30 plus 1/90.